Okay, now we have derived all the forces acting on the fluid element. Let's write the Navier-Stokes equation. So we we said that delta V is the volume, which is delta X, delta Y, delta Z, and delta M is the mass, which is rho times delta V. And according to Newton's second law, delta M times the acceleration is equals the sum of forces acting on the fluid element. So delta M can be replaced by rho times delta V, then rho times delta V, and the acceleration by the material derivative, the velocity dv over dt equals the first force we derived was the body force, or body force due to the gravity, the gravitational force, or times g times delta v minus the pressure force term, which is nabla p times delta v plus the viscous force term mu nabla squared v. Then get rho delta v. So the material derivative can be decomposed into the local derivative and the convective derivative. Then we get partial v over partial t plus v dot nabla v equals rho times g delta v minus nabla p times delta v plus mu nabla squared v. Yeah, there was delta v here, delta v. So since we are working with the same volume, delta v cancels out. So the equation becomes rho times partial v over partial t plus v dot nabla v equals rho g minus nabla p plus mu nabla squared v. So This is the Navier-Stokes equation. This is the Navier-Stokes equation in general form, and we assume this is for incompressible fluid, compressible fluid. So if the viscous effects are neglected, the Navier-Stokes equation reduces to the Euler equation. If mu equals 0, the Navier-Stokes equation reduces to the Euler equations. Then we get, this is if mu, let me get rho times partial v over partial t plus v that nabla v equals rho g minus nabla p. So this is Euler equation. So thank you for watching. See you in the next video for